For our next question, we have a 75 kilogram mass suspended from a ceiling by two lengths of rope, making angles of 50 degrees and 35 degrees with the ceiling. We need to determine the tension in each rope. So, for the first step that we do is to draw a representation of the ropes with the weight. The ropes are making 50 degree and 35 degree angles. And I'm just going to suggest that this will be rope 2 and this will be rope 1. I'll just call it R1 for now. Now, what we see then is that we're going to have a number of different forces acting on this weight. Specifically, we're going to have the weight of gravity acting downwards, because the mass weighs 75 kilograms. And there's going to be tension going up the length of each rope. There's going to be some tension up this rope and some tension this way. So what we have is a situation with three forces, and those forces are in equilibrium. We know that because the weight itself is stationary. It's not moving. So these three forces must all, in a sense, close off a triangle. Here's what I mean diagrammatically. If we take these three red vectors and move them around so that they reveal equilibrium diagrammatically, we get something that looks like this. Our force in a downward direction is the force of gravity. We'll call that G. We'll call the tension in rope 2 T2, and we'll call the tension in rope 1 T1. And remember what we said about vectors. They have a magnitude and a direction, but they don't have a fixed location, and so what we can do is move them around appropriately, head to tail, so that they close off the system and we have equilibrium. Equilibrium frequently looks like, for lack of a better term, a closed triangle, or polygon if there's more than three vectors at work. So, going back to our original diagram, we see that we have T1, which is the tension in rope 1, will make a 50 degree angle with the ceiling. T1, the vector, will make a 50 degree angle with the ceiling. Okay? Similarly, T2, the vector, makes a 35 degree angle with the ceiling, as revealed in the diagram here. So we're going to have in our diagram, T2 make a 35 degree angle with a horizontal line. It doesn't show up very well right now, but that's a 35 degree angle. And because this horizontal line and this horizontal line are parallel, we see that this angle here above the horizontal line must be equal to 50 degrees due to the Z pattern. So what I like to do at this point is make a new diagram, and with clearly indicated angles, and here it is. We have an 85 degree angle here and a 40 degree angle here. We know that because the 50 degree angle must lead to a 40 degree angle in here. 35 plus 50 is 85, and that means that the third angle here must be a 55 degree angle. And we're now in a position to determine the magnitude of each of these vectors. Well, we know that the weight, the force due to gravity is equal to 9.81 newtons per kilogram in a downward direction. So we can say that the magnitude of G is 75 kilograms times 9.81 newtons per kilogram, which is 735.75 newtons. We can then set up the sine law. We're going to find the magnitude of T1. So we can say that the magnitude of G over sine 85 is going to be the magnitude of T1 over sine 55. From there, it just becomes some simple arithmetic. And we get a final answer of T1 being approximately 605 newtons. We can then determine T2 by setting up a similar sine law. The magnitude of T2 over sine 40 is the magnitude of G over sine 85. Plug in some numbers and determine that the tension in the second rope must be approximately equal to 475 newtons. That leads us to our final statement, therefore statement, which is that the tension in the rope 50 degrees to the ceiling is approximately 605 newtons up the rope. We need to say up the rope because tension is a force and force is a vector and vectors require direction. And similarly, the tension in the other rope is approximately 475 newtons up the rope.